Once again, I'm Derek, Application Chemist for Consumables from Shimadzu Asia Pacific. It is my pleasure to be here today to share with you some of the parameters that affect your LC column performance. And for this webinar, we will be mainly focusing on the most commonly used column, which is the C18 columns. There are so many different C18 columns out there, and even from the same manufacturer, there are multiple different types of C18 columns. So what are the differences between them? In this presentation, you will be seeing why some of these C18 columns may look very similar from their description, but are actually performing very differently. Before going into the details of the columns, let's take a step back and look at the HPLC system as a whole. Many of us is probably very familiar with the components in a HPLC system. Typical HPLC system will consist of a mobile phase reservoir that holds the mobile phase solvent. We will also have a pump that delivers the solvent, and an injector is also required for the introduction of the liquid sample into the system. Your sample will then be separated in the column before eluting out as separate components and detected by the detector. What I would like to highlight is that in chromatography, the objective is to separate components in a mixture. And in HPLC, the separation occurs only in the column. You can have the most sophisticated system, but without a column, there is no chromatography. The column is what makes the most difference in a separation. So it is important for us to understand the characteristic of a column so that you can choose an appropriate column for your analysis or optimize your separation. There are many properties to take note of when it comes to LC columns. If you have an LC column with you and you look at the label on the column or on the box itself, you will find that some of these properties are written in the description. For example, what I have shown here is the label for our SHIMPAC GIST column. What you could find are information such as the phase, which is C18 in this case, the particle size, which is 5 micron over here, and the physical dimension of the column, which is written as the internal diameter by the column length. This is pretty much what you can find on the label for most columns. However, there are many more properties of the columns that can affect your separation, and they are usually not written on the label. Properties such as pore size, surface area, carbon loading, and end capping. In Shimadzu, you can find all this information for whichever Shimadzu column on our online web store, Shop Shimadzu, which the link you can find over here. Differences in these properties can result in very different separation profiles, and we shall see how each of these properties affects your separation. We will start with the physical dimension, the length, internal diameter, and the particle size. These are the properties that you can easily find on the label. Then we will move on to the rest of the properties that are often neglected, including pore size, surface area, carbon loading, and end capping, before coming back to the different C18 phases, and lastly, the particle size, which is equally important, but many of us often does not pay much attention to. Let's start with the column length. The column length has a direct relationship to separation resolution. If you have two closely eluting peaks that you wish to separate, for example in this case where we are using a 100 mm column, the two peaks are closely eluting but not baseline resolved. What you can do is to change to a longer column, for example a 250 mm column, and you can increase the resolution between the peaks. However, it should be noted that the increase in resolution is not linear, meaning doubling of the column length does not double the resolution. So you may think, in that case, it should be better for us to always use a longer column. But that is not true. there are consequences to using a longer column. The column pressure will be higher for longer column, and if you notice, the analysis time would also increase, which will also increase your operation cost. On top of that, longer columns are also much more costly. So if your peaks are well resolved and there is no need for additional resolution, you should avoid using a longer column. The next physical dimension is the column internal diameter, or the column ID. The column ID determines the maximum loading capacity of the column. A larger ID column would have a higher loading capacity, but you would also need a higher mobile phase flow rate. For example, if you are running a 0.4 ml per minute for a 3 mm ID column, to get a similar separation, you will need to run your analysis at 1 ml per minute for a 4.6 mm ID column because of the increase in cross-sectional area of the column. It can be for various reasons that you want to change the column ID. For example, moving from analytical to preparative separation, or maybe reducing the column ID to reduce operation cost. In such case, it is likely that you would want to get a similar separation between the columns of different ID. It is therefore important to maintain a constant linear velocity when changing to columns of different sizes. Here is the formula for calculating the linear velocity. The linear velocity is equals to the analysis flow rate divided by the column cross-sectional area. So if you are using a 4.6 mm ID column, the cross-sectional area would be a 16.6 mm square. And a 3 mm ID column would have a cross-sectional area of 7.1 mm square. If you are running at 1 ml per minute on a 4.6 mm ID column, you would then need to run a 0.4 ml per minute on a 3 mm ID column in order for you to maintain a constant linear velocity and a similar separation profile. Here is an approximate loading capacity of different ID columns. Do note that the actual loading capacity still depends on the property of the analytes. Smaller ID columns are usually used for analysis such as qualitative and quantitative analysis, while larger ID columns, which we usually call them preparative columns, are typically used for purification of compounds. Next, we have the particle size. Column efficiency is inversely related to the particle size, meaning peaks would be sharper, resolution would be higher when using a smaller particle size column. This would also mean that you can have the option of maintaining the column efficiency by using a smaller particle size column, but with a shorter length. This way, you can actually reduce your analysis time and increase your throughput. As technology of HPLC instrument and column packing techniques advances, columns with sub-2 micron particles are now available. While there is certainly an advantage of using smaller particle size columns, there is also drawbacks associated with it. The column pressure will increase with the decrease in particle size. So you would have to ensure that your HPLC instruments are able to handle the higher pressure associated with smaller particle size columns. Pore size also plays an important role in separation, especially when you are separating molecules with larger size. Most of the stationary phase groups are located inside the pores of the particle, so molecules need to enter the pores for an effective interaction. In order for the analytes to enter the pore size needs to be larger than the analyte's molecule. If your analyte is larger than the pore size, the interaction with the stationary phase will be limited, and the separation will be poor. As a general guideline, when analyzing small molecules of less than 2000 daltons, columns with pore size less than 20 nanometer is good enough. But for larger molecules that are more than 2000 daltons, such as biomolecules, a larger pore size column of more than 20 nanometer would be more appropriate. For example, our Shimpact GISS C18 column has a pore size of 20 nanometer, and our Shimpact Scepter C4 column has a pore size of 30 nanometer. Other than the size of the pores, the number of pores is also important, because this determines the surface area available for interaction with the analytes. Surface area is defined as the area of the silica that can be in contact with the sample. With an increase in number of pores, the surface area will increase. The overall effect is an increase in retentivity because the analytes will have more surface area for interaction. If you need to improve your retentivity of your analytes in the column, a larger surface area column should be chosen. Carbon loading is one of the parameters that is often neglected. Carbon loading is defined as the amount of bonded phases attached to the support material. For example, in C18 column, a lower carbon loading would mean that there is lesser C18 group attached. So what is the consequences? If we look at the chromatogram over here, a low carbon loading column such as the Shimpact GISS C18 column would have a lower retentivity as seen in the shorter retention time. This is because there is lesser C18 group for the analytes to interact with as compared to a higher carbon loading column such as the Shimpact GIST C18 column. This means that you can reduce your analysis time and increase your analysis throughput when changing to a lower carbon loading column. However, you should note that the resolution value will also decrease. So decreasing the carbon loading will not be good if you do not have enough resolution to sacrifice for a faster analysis. Another parameter that we are looking at is end capping. End capping is a treatment to reduce unwanted interaction of analytes with free silanol group on the silica particle. During the manufacturing of the column, take for example, a C18 column, the surface of the silica particle is modified by reacting with C18 groups. However, the reaction would never be completed, and there would always be free unreacted silanol groups remaining. These free silanol groups can cause adsorption of basic compounds, for example, compounds with amino groups, which can result in pigtailing problems. To reduce this effect, one of the ways is to perform end capping. End capping covers the free silanol group, usually by reaction with trimethylsilyl chloride, preventing the unwanted adsorption effect. Columns that are not well end capped will face problems of pigtailing for basic compounds such as dextromethamphetamine, which has an amino group. You can see from here that these problems are observed in some of the competing brand C18 columns such as the X-Select CSH C18, Zorbex Eclipse Plus C18, and Luna C18 columns, while our Shimadzu Shimpact GIST C18 columns, which is well end capped, does not have this problem. Having said that, there are still columns that are not end capped which utilize the residual silanol activity for separation. Now all these properties that we have gone through so far can be found on our Shop Shimadzu website, including the properties that are found on the box or on the column label itself. We are still left with the last property, the phase chemistry, which is largely determined by the bonded functional group. Phase chemistry is what makes the most difference in your separation, and it goes beyond just the bonded functional groups. There are many different phases in LC column. Few of the most commonly used ones are listed here, which includes the reverse phase, normal phase, helix mode, ion exchange, and size exclusion. In this presentation, we will only be focusing on the reverse phase and more particularly the C18 columns. Reverse phase columns has a non-polar stationary phase. Example of reverse phase includes C18, C8, phenol, and pentafluorophenol. They typically uses a polar mobile phase such as water with water miscible organic solvent such as methanol or acetonitrile. The elution strength can be increased by decreasing the mobile phase polarity, meaning increasing the organic content in the mobile phase. Generally, the more polar analytes will elute first, but this can also be affected by the additional interaction offered by different phases. In this presentation, we will only be focusing on the C18 columns. C18 columns are the most widely used LC columns. They are bonded with linear chain of 18 carbon, which are also called octadecyl, or in short, ODS. So you may find that some of the column phases are indicated as ODS instead of C18. The main interaction with the analytes is through hydrophobic interaction. While C18 columns are considered general purpose columns, there is still a wide variety of them, and not all of them are the same. Additional selectivity can be introduced by modification of bonded C18, or having changes in the way the C18 groups are bonded. For example, steric selectivity can be introduced by using polymeric bonded C18. In typical C18 column, such as Shimpack GIS C18 column, the C18 group is usually monomeric bonded, meaning each silica atom only has one C18 group bonded to it. They are more spaced out, so molecules, regardless if it is planar or non-planar, can move in between the C18 groups for interaction. In polymeric bonded C18 columns, such as the Shimpack GIS C18P column, each silica atom is bonded with more than one C18 group. So there is smaller space between the C18 alkyl chain. Planar molecules are able to slide in between this small space and interact with the phase, while non-planar molecules would have more difficulty entering these small spaces and will thus experience lesser interaction. This creates the effect of steric selectivity that can help with separation of compounds with very similar hydrophobicity. Take, for example, the separation of vitamin D2 and D3, which differs in a methyl group. Using the monomeric bonded Shimpack GIS C18 column, the two peaks are not completely resolved. However, with the help of steric selectivity in the polymeric bonded Shimpack GIS C18P column, baseline resolution can be achieved. The steric selectivity properties of Shimpack GIS C18P column is useful for analysis of polycyclic aromatic hydrocarbon, or PAH, where the separation of planar and non-planar molecules is needed. Another property that you have to be very cautious of is aqueous stability, because not all C18 columns are stable under fully aqueous condition. A phenomenon called phase collapse can occur when using fully aqueous condition on a non-aqueous stable column. For non-aqueous stable columns, under normal condition containing organic solvent, the bonded C18 phase are solvated and distributed. However, if 100% aqueous condition was used on such column, the C18 phase being hydrophobic dislikes the aqueous condition They will then fold upon each other and force the solvent out of the pores. This will damage the column because your analytes will no longer be able to enter the pores where most of the C18 groups is located. So there will be no interaction and thus no separation. So always to use an aqueous stable column if your analysis method starts with fully aqueous mobile phase to prevent hydrophobic collapse. Some of the Shimadzu aqueous stable columns include the Shimpact GIST C18AQ, Shimpact GISS C18, Shimpact GIS RP Shield, and Shimpact Scepter C18. Each of these columns has their unique properties besides being aqueous stable. For example, the Shimpact GIS RP Shield column is another type of C18 columns called the polar embedded C18 column. A polar functional group is embedded between the silica surface and the C18 phase, making it stable for fully aqueous condition. The polar functional group also provides additional hydrogen bonding interaction with analytes that are able to interact via hydrogen bonding. For example, these four compounds, benzyl alcohol, aniline, phenol, and nitrobenzene, are not well separated by other reverse phase columns such as C8 and phenol column, but can be separated with the help of hydrogen bonding interaction on a Shimpact GIS RP Shield column. Highly polar compounds are difficult to retain by reverse phase columns. They usually elute very early on reverse phase columns. Our Shimpact GIST C18AQ column is designed to provide enhanced retention of polar compounds on C18 phase columns. Bonding of C18 groups are optimized to not only provide maximum hydrophobic interaction with the analytes, but also give stability to fully aqueous condition. If we look at the chromatogram over here, we can see a great improvement in retention compared to ordinary C18 columns such as the Shimpact GIST C18 column. The increase in retentivity is much higher compared to other competing brands such as the Atlantis T3 columns that are made with a similar concept. We have now seen many of the C18 columns, each with their unique properties. Here is a short summary highlighting the key features of each of these C18 columns that we have seen so far. The C18 columns that I have introduced so far are what we call the fully porous silica column. Shimadzu also offers C18 column based on other particle types, which gives other favorable properties to the column. And this brings us to the next part of this presentation on the particle types. There are generally two types of particles that are commonly used in HPLC columns. They are either packed with polymer or silica particles. Polymer particles are more commonly used in columns such as ion exchange, gel permeation, and gel filtration columns. Silica-based columns, on the other hand, are much more widely used and are involved in many applications. In this presentation, we will only be focusing on the silica particle C18 columns. Within the class of silica particles, we can further classify them into fully porous silica particles, which includes the columns that we have seen so far, such as the Shimpact GIS and Shimpact GIST columns. They have a longer history, so many applications are based on these types of columns. In recent years, we have seen an increase in popularity of other silica types such as the fully porous organic silica hybrid column and also the superficially porous, or also commonly known as core shell columns. These are our Shimpact Scepter and Shimpact Velox series respectively. We will now look at what are the differences between them. First, we have the fully porous silica particle columns. The fully porous silica particle is the most traditional particle types which are still being used today. They are well established and has a wide variety of different phase chemistry available. However, they usually have a limited pH stability range, usually around 2 to 8 for a standard C18 column, while higher purity silica can withstand larger range of pH of around 1 to 10. This is because under highly acidic condition, dissolution of bonded phase will occur, causing the loss of the stationary phase. You will start to see reduction in retentivity of the column, and eventually the column will become damaged and you would have to replace the column. On the other hand, when exposed to highly basic condition, the dissolution of the silica will occur. This will cause dead volume in the column, and you will start to see problems such as increase in column back pressure and distorted peak shape. The damaged column will then have to be replaced. So it is important for you to work within the recommended working pH range of your column. If your analytes are ionizable, the ionization state will affect its retention. So the retention time can change depending on the pH of your mobile phase. Basic compounds are generally neutral at higher pH and will thus retain longer in the reverse phase columns as compared to when they are in their charged state at lower pH. So adjusting pH can be a strategy for altering the retention of compounds to achieve a better resolution. However, the stability of fully porous silica particles is generally limited at higher pH. This is where organic silica hybrid particle columns has the advantage. And this brings us to our organic silica hybrid column, our SHIMPAC scatter series. In the event that you need a wider pH range for your analysis, our SHIMPAC scatter series, which is packed with fully porous organic silica hybrid particles, would be the ideal choice. For SHIMPAC scatter C18 column, it has the expanded pH range of 1 to 12 for a C18 column. One application that requires such high pH stability is the separation of oligonucleotides. In the chemical synthesis of oligonucleotides, the final step, which is the deprotection step, is usually achieved under highly basic conditions such as in ammonium hydroxide solution. So a column that can withstand high pH is required to ensure that the column is not damaged by any residual ammonium hydroxide. On top of that, at low pH, depurination reaction can occur that degrades the oligonucleotide. Here you see the separation of oligo-DT ladder with one nucleotide difference using the SHIMPAC scatter C18 column. In addition to the wide pH range, there are many chemistry lineup in the SHIMPAC scatter series, which is perfect for method scouting. This makes them the most versatile column available. Here is an example. With the various phase we have and the wide pH range of SHIMPAC scatter series, method scouting can be easily performed to identify the best condition for your separation by varying not only the stationary phase, but also the pH of the mobile phase. As we are focusing on C18 column, you may have noticed that our SHIMPAC scatter series have two different types of C18 columns. So what are the differences between them? The main difference is the density of C18 groups that are bonded. Both of them have a wide pH range of 1 to 12. However, the SHIMPAC scatter HD-C18 has a higher surface area and carbon loading due to the higher density of C18 groups. Also, because of the high density of C18 groups on the SHIMPAC scatter HD-C18 column, it also provides a steric selectivity. Take for example, the separation of vitamin D2 and D3, which is not well separated on our SHIMPAC scatter C18, can have a much better resolution when using a shim-packed scatter HD C18 column owing to its steric selectivity. There may also be a situation where you want to reduce your analysis time to increase your analysis throughput. When it comes to speed of analysis, column with core shell type particles would be the best choice. This type of particle has a non-porous core that is covered with a layer of porous silica. And the column with such particles are represented by our shim-packed Velox series. It has several key advantages over the more traditional fully porous silica particle. It displays higher column efficiency and resolution. So you can have the option to maintain your resolution by using a shorter column length, which helps to reduce your analysis time and increase your analysis throughput. Additionally, unlike methods to increase resolution such as increasing column length and reducing particle size, which cause column back pressure to increase, core shell particles allows increase of resolution without much change of the column back pressure. So how is this achieved? To understand this, we first need to know what the column efficiency depends on. The column efficiency is governed by the Van Dimter's equation, which describes the column efficiency as high equivalent theoretical plate, or HETP. The lower the HETP, the higher the efficiency of the column. HETP depends on three coefficients: the A term, which is the eddy diffusion term, the B term, which is the longitudinal diffusion term, and lastly, the C term, which is the mass transfer term. The A term describes the path taken by the analytes when passing through the column. This depends on the quality of the column packing. The more evenly the column is packed, the smaller the A term will be. It also depends on the particle size. The smaller the particle size, the more even the packing can be. So there will be lesser difference in the path that an analyte can take, which translates to a smaller A term. Unlike traditional fully porous particle, the core shell particle has a much tighter control of the particle diameter. So the column can be packed more uniformly, which, if you recall, is what causes the reduce in A term. The B term describes the diffusion of analytes away from the concentrated center of the zone, and it depends on the void volume. One of the ways to reduce B term is to increase mobile phase flow rate so that the analyte spends lesser time in the column, and there will be lesser time for the analytes to diffuse. But this will also mean that there will be lesser time for the interaction with the stationary phase, and there will be lesser separation. So there is only a limited window for adjustment of mobile phase flow rate. The other method to reduce B term is to reduce void volume, and this is exactly what the core shell column does. Because the center of the core shell particle is non-porous, the pore volume and thus the void volume is lower compared to the fully porous particle, and this greatly reduces the longitudinal diffusion B term, improving the column efficiency. Lastly, we have the C term, which describes the diffusion of analytes between mobile phase and the silica pore. In fully porous silica particles, analytes can reach a greater depth into the particles, causing a higher mass transfer term. In contrast, in a core shell particle, the center core is non-porous. So the mass transfer is limited by the depth of the outer porous layer, leading to a lower C term for a core shell particle. All of this together allows core shell columns to achieve a higher efficiency. If you look at the Van Dimter's plot over here, you can see that a 2.7 micron core shell columns can reach the efficiency equivalent to that of a 2 micron fully porous particle column. And that is not all. the column back pressure is less than half of that compared to a 2-micron fully porous particle column. The high column back pressure associated with a smaller 2-micron particle size column will require the use of UHPLC system. But with the core shell column, the same efficiency can be achieved using a larger 2.7 micron particle size column, which gives a lower back pressure that is manageable on a normal HPLC system. Here is an example where you can see that a 2.7 micron core shell column can achieve an equivalent performance with the similar theoretical plate count as the 2 micron fully porous particle column in much shorter time, and all of these at only half the column pressure. Some practical example includes high-resolution analysis of 24 different preservatives commonly used in cosmetics in just less than 9 minutes. And also the high-resolution analysis of 23 different regulated UV absorbent commonly used in cosmetics in less than 18 minutes. We have various phases available in our Shimpact Velox core shell series, and you will probably have noticed that we have actually 2 C18 phases available. While both columns are core shell C18 columns, the Shimpact Velox SP-C18 is theoretically protected, allowing a lower pH stability of 1 to 8. With that, I'm almost at the end of my presentation. A short recap of what we have discussed. There are several factors that affect the performance of a HPLC columns, and many of these parameters are not stated on the label for the column. You can always check the rest of these parameters on our Shop Shimadzu online web store. For column length, we see that longer columns will result in higher efficiency and also an increase in resolution. But it also will cause back pressure to increase, and the analysis time will also be longer. The column internal diameter, or ID, affects the sample loading capacity. Larger ID columns are usually used for preparative purification of compounds. It is important to maintain a constant linear velocity when switching to columns of different ID in order to obtain a similar separation profile. Particle size affects the column efficiency. Smaller particle size gives higher efficiency, but you would have to take note of the increase in back pressure and ensure that your instrument is able to handle it. Selection of pore size is critical when separating larger molecules such as biomolecules. Be sure to use large pore size columns when analyzing large molecules. Surface area and carbon loading both affect the retentivity of the column. Columns with higher surface area and carbon loading will have higher retentivity. Conversely, if there is enough resolution, you can choose a column with lower surface area and carbon loading for a faster analysis. When analyzing basic compounds, columns that is end-capped will prevent pigtailing, ensuring a symmetrical peak shape in your chromatogram. The phase chemistry is what makes the most difference in separation. We see that even for the most widely used C18 columns, there are many different variations that can have an advantage in certain applications. One of the points to take note is the column stability to fully aqueous condition. Never use 100% aqueous condition on a non-aqueous stable column to avoid phase collapse. Lastly, we saw the different silica particle type. Fully porous silica particles are the most traditional particle type which are still commonly used today, while the newer organic silica hybrid column which has the key property of wider pH range, is also becoming more common. The core shell type particle has the advantage of faster analysis, higher efficiency with significantly lower back pressure, and is becoming more popular for high-speed analysis. With that, I've come to the end of my presentation. Thank you for your attention.